You're going to think rate of change in energy storage means watts in general, okay, and the heat equation is in units temperature over meter squared. It's not in watts. So I can't work with the heat equation in this case. I need to work with some equation in the terms of watts. So that's what we're going to do here to solve for this rate of change of energy storage in the wall. So we have our energy balance, and now what that's going to go to is a balance of the energy over the entire system. It's the entire plane wall. And we just calculate the heat rate entering the entire plane wall, and we calculate the heat rate leaving the entire plane wall. So that's going to be our E in minus E out. Because we know Fourier's law is in units of watts. We're looking for some things to plug into here in units of watts. So bam, this is what we get. E in capital E dot in minus capital E dot out goes to Q in minus Q out plus our energy generation, Q dot times the area times the length times the volume, basically. This is moving this from watts meter cubed to watts, equals the energy storage rate. And carrying it even further, we get this. So here we just plugged in what we had from up here, in for Q in minus Q out, and we basically solve our equation for the rate of energy storage in watts. So there was the solution to part 2. So we have one more, part 3. Now we need to know a temperature. We want to know the rate, time rate of temperature change at position x equals 0, so on and so on. But we're going to solve it generally. So we're going to have this equation, and this is just rearranging our heat equation. We made assumptions about it being one-dimensional and so on. So this is the same heat equation, just rearranged so that the change in temperature with time is showing up on the left-hand side. Your left, all right. And basically, that equals this relation. Because now we see that the change in temperature with time equals these constants. And these are constants too. But these constants times the partial derivative, second order partial derivative of t with respect to x. So that's how we solve for our temperature, time rate of change of temperature at x equals 0. So a take-home message is that Fourier's law can always be used to compute the conduction rate from knowledge of the temperature distribution. And I already said this, but it's worth reiterating. Even for unsteady conditions and when heat generation is in the problem. It doesn't matter. If you know the temperature distribution, you can apply Fourier's law and determine the conduction heat rate. So here's another example. I told you there are 2 types of problems that you'll encounter working with the heat equation. 2 primary types of problems. There may be some other corollary type problems, but these are the main 2. And in this example, we have a plane wall once again, and it's initially at a uniform temperature, and it's suddenly exposed to convective heating at one surface. And now what we want to figure out, this is the problem where you're just given a description and you have to choose the appropriate form of the heat equation to apply. So the first thing we want to do is we want to figure out what the form of the differential equation, the heat equation, should be and which boundary conditions we need. Then we're going to sketch the initial and steady state temperature in 2 intermediate times. We're going to do some more sketching, and then we're going to look at what the total energy transfer to the wall is. So here's our picture. We have a wall that is insulated on one side, and then it has a convective boundary condition on the other. So where it's insulated, these are boundary conditions. This is a boundary condition of what type? First, second, or third type? So this is the boundary condition of the second type, where Fourier's law or the temperature gradient equals 0. Everything's going to flat. And here where we have the convection coefficient, this is the boundary condition of the third type, so it's mixed. Fourier's law going out, balanced with Newton's law of cooling. There. So draw your own schematic. The book puts schematics up, but you want to draw your own schematic, make it as detailed as you need it to help you with the problem. And we show the same type of things here. So our assumption is about this problem are similar to the last problem. We have 1D conduction in the x direction. We have an isotropic medium with constant properties. But in this case, we have no heat generation. There's no heat generation. So what does that look like? Well, here's our general heat equation. In units, K per meter squared. And I always talk about units. I talk about them because they're important. I think they help you solve a problem if you keep track of them. So this is K per meter squared. And we have our assumptions 1D, isotropic, and no heat generation. Well, we already showed this equation in the form that's isotropic. But we have to now get rid of a couple of dimensions and get rid of heat generation. And that's what we did. So now that goes to this simplified version. This is a 1D transient heat conduction equation. And that would be the appropriate equation for this problem. And we now need boundary conditions. So if we have a 1D transient conduction equation, second order in x, first order in time, this means we're going to need two boundary conditions and one initial condition. So our first boundary condition is what I've already mentioned, insulated, meaning that the temperature gradient is 0 at x equals 0. The second boundary condition is the mixed boundary condition, where we have our heat rate leaving the wall at x equals L equals to the heat rate that's convected off the wall. They have to be equal with that boundary. The heat entering to leave the wall, we're entering the wall, I'm sorry, and then the heat leaving the wall through convection. They have to be equal. And then finally, we saw the problem, we needed an initial condition. So initially, this wall at any x at time 0 is at a temperature Ti. So here it's Ti, it's the initial temperature. So that's solving the first part of this problem. Basically, working with the heat equation, identifying which parts of it we're going to keep, which parts we're going to throw away, knowing which boundary conditions we need to apply. We need to be able to do this not only in Cartesian coordinates, but in cylindrical coordinates and spherical coordinates as well. So now we're going to move on to the second part. So here we want to sketch the initial and steady state temperature distribution and two intermediate times. So I'm going to move up the projector. We go ahead and erase this artifact. All right, so I'll let you some space in your notes to work along with me. So here we have, let's say this is temperature, and this is position X in the wall, right? So initially, before the convective heating starts, our wall is at an initial condition. We already said initial temperature. We already said we had an initial condition where that wall is at a uniform temperature. So this is at T, at any X, at T equals